Good morning, everyone. I, Gaura Saxena, on behalf of GRIHA Council, would like to extend a very warm welcome to everyone for the session on sustainable cooling alternatives. This session shall lay emphasis on the policies focusing on cooling, their implementation and challenges, various cooling technologies suitable for India, alternate methods, best practices, and strategies to reduce greenhouse gas emissions through efficient cooling, and access to affordable, sustainable cooling solutions for all. So, since our esteemed panelists are already on the dais, I would would like to introduce them. Mr. Saurabh Kumar, the Managing Director of Energy Efficiency Services Limited, Delhi. Mr. Markus, Wypior, Deputy Cluster Coordinator, GIZ. Dr. Anir Upadhyay, Research Fellow, Faculty of the Built Environment, University of New South Wales. Mr. Sunil Kher, Managing Director, Sevcon India Private Limited, New Delhi. Mr. Shadab, Ahmed, National Manager, Defense and Government Segment, Indian South Asia, Armacell. Let's extend a warm welcome to all our speakers. I would now like to take the opportunity of introducing Mr. Saurabh Kumar. Mr. Kumar is an IRS officer of 1992 batch. He has worked in various capacities in Income Tax Department, Ministry of Power, and Bureau of Energy Efficiency. He was Secretary BE during 2007 to 2010. It's an honor to have you here, sir. I would request Mr. Saurabh Kumar to deliver the thematic address.
Thank you very much. Mr. Markus, Wypior, fellow panelists, Mr. Sanjay Seth, ladies and gentlemen. First of all, let me thank 10th GRIHA and Mr. Sanjay Seth in person for bestowing this honor on us, inviting us here on this. And the topic today, of course, is an extremely important topic in more ways than one, because it links up a lot many things that we are now going to see as India develops. To begin with, what I would like to mention is the India that will stand in 2030 70% of it is yet to be built. That's number one. Number two is we will have at least 10 to 15 mega cities. And by mega cities, I mean cities which will have more than 50 million population. No country in the world has ever handled or planned or delivered a mega city of that magnitude. So that is the second thing. The third thing which comes out of a report which was initially done by the Lawrence Berkeley National Lab, which has also found a mention in the National Cooling Action Plan that the Government of India has released, is that the cooling demand in the country, just the cooling demand, would require 150 gigawatts of additional incremental capacity. Whether it comes from renewables, whether it comes from fossil fuel, it's a separate matter. The fourth thing is, with this kind of surge in demand, we are also mindful of India's commitment to the Montreal Protocol, where you have to phase out HCFCs in the next decade or so, which actually is the same time frame in which you have to cater to a massive surge in demand for cooling. So these are all challenges. These are all issues that need to be taken note of. And I think events like these, discussions where experts from India and elsewhere sit together, deliberate, and figure out what is the best trajectory of growth in this sector. So clearly, let me put together what we in ESL think should be the way this demand needs to be managed. And I'll put this in two categories. One, of course, is the consumer segment, which will grow perhaps much faster than the commercial and other segments. The room air conditioners, for example, which we are already witnessing about 15% growth every year, and with the country with GDP rising at over 7%, we would perhaps see a much larger growth in the coming years. So, taking note of that, we have begun a program for super efficient air conditioners, as we call it. We did a procurement of about 100,000 air conditioners a couple of years ago. We demanded air conditioners that were at least 40 to 50% more than the highest or best in class available in the market. And while many people said that you will not get any, but the fact is we did, and we got it at a very reasonable price. And what we are also seeing, and I don't know whether that procurement was a catalyzing force or not, or it was just a coincidence, that one of the major air conditioner manufacturers announced last year that it will only go in for inverter models. It will not do anything, will have anything to do with the fixed compressor models. And we have seen in the last 1 year that the baseline energy efficiency of air conditioner improving. What is needed, therefore, is a big policy push from players like Bureau of Energy Efficiency to basically enhance the ambition of the labeling program. We asked for an air conditioner which had an ISEER of 5.3 2 years ago. At that point in time, the Bureau of Energy Efficiency 5-star label was 3.7. Today, in the international market, we have air conditioner at ISEER nearing 8. I mean, what is the reason for not upping the ambition from the policy standpoint? The oft-repeated argument that air conditioners, if you have efficient air conditioners, it leads to increase in cost. That is absolutely incorrect if you look at empirical international data. And I'll quote two of the data. In Japan, the energy efficiency of air conditioners increased by 200% in the last 2 decades. The real cost actually went down by 30%. Look at India's program. The labeling program in India started somewhere in 2008. We are 10 years from now. Our baseline efficiencies have increased by about 40%. The real costs have not risen, actually gone down. I mean, I'm talking about cost adjusted with inflation. So it's actually a myth that if you have more efficient air conditioners, it will lead to increase in cost. So my first, food for thought that I will probably ask the experts here is to build around the technical model that we need to significantly increase the trajectory of efficiency for particularly room air conditioners. We have the golden opportunity of changing and leapfrogging to technologies that other countries did not have the luxury of. For example, Germany. I mean, Germany never had a 5.3 ISEER air conditioner when it was growing at the stage that we are growing. But India certainly has that luxury, if I may be allowed to say that. And it is therefore incumbent upon the policymakers and regulators to seize this opportunity and turn the trajectory around. The same LBNL report says, if this trajectory moves to a super efficient level, the 150 gigawatt can actually come down to 80 gigawatt. Now that's a massive, massive savings in terms of costs, in terms of the externalities of environment, etc., etc. The second thing is a lot of commercial area also will be built as India grows, and we are already seeing construction almost everywhere that we go in this country. And just before the session, I and Markus were discussing about district cooling. Now that's something which needs to come in, particularly in the new infrastructure that is getting built. Number two, we are seeing a lot of natural gas coming into the Indian market. The government has already auctioned about 89 cities for city gas distribution. There is plenty of domestic gas which has been discovered. And one of the, and we recently signed up an MOU with the Gas Authority of India Limited and their city gas services, essentially to push in trigeneration as a service. Trigeneration, I'm sure most of you are aware about, but let me just very quickly brief this. And this is something that Bureau of Energy Efficiency started off when Mr. Seth was there, along with GIZ, as a pilot project in All India Institute of Medical Sciences. What it does is a very simple thing. Puts up a gas engine, provides electricity to that commercial building through the gas by conversion from gas to electricity. The waste heat that comes out is trapped into a cooling through a vapor absorption machine. And you also have a 70-degree water. So wherever you have three forms of energy, and these are hotels, hospitals, shopping malls, airports, industries which have waste heat generation, all these places can actually reduce their energy cost by as much as 50%. I'm not sure how many people are aware of the fact, and I'm sure all of us must have been there, is the DLF Cyber City in Gurgaon, which has fantastic restaurants, and it is run by a 40-megawatt trigeneration plant. It is not connected to the grid. Yes, it is owned by DLF itself. And there are few other isolated examples of such projects in Delhi. We have taken upon ourselves to push this as much as we possibly can. We are doing this because of the fact that we acquired a company in UK, which actually specializes in exactly these kind of integrations. Of course, in UK, it is not trigeneration, it is largely combined heat and power. It only is able to, is required to trap the waste heat for heating. And we are about to sign a couple of projects in Mumbai, basically for implementing these in industries, in hospitals, and we are also working on a large number of similar projects across the country. The near-term potential of trigeneration is about 15,000 megawatt in all these things. It also does away with the myth that gas-based generation, power generation is very costly. It is not. In fact, the service model that we have proposed and which has been accepted by several clients is that if you are paying your electricity bill for all these services, let's say that electricity cost comes to X, we will give you exactly the same facilities in 0.8x. And the reason why this is not costly as compared to grid is that the conversion efficiencies go up to about 90%. In a standalone gas generation, the conversion efficiency is only 40%. And that is primarily the reason why these become affordable. And of course, it augurs very well for cities and mega cities that are coming up like Delhi. And let me very quickly, as I conclude, give you an example with numbers for Delhi. Delhi's peak demand last year was 6,000 megawatt. This year, the year that is currently we are in, the peak demand rose to 7,500 megawatt. 90% of the incremental demand was cooling. Now, while we may say that we have enough surplus capacity to provide Delhi that 7,500 megawatt, which is expected to rise to 8,500 to 9,000 megawatt in the coming year. But does the utility, the BSES and Tata Power, do they have the requisite distribution infrastructure to push that much of demand? Because it requires wires, it requires space, it requires transformers. So the thing is, while many DISCOMs still feel that localized generations like trigeneration could actually hurt their consumers, but the fact is, if you look at a cost economic analysis of investing in new infrastructure, and particularly new cables, new transformers in a city like Delhi or Mumbai, versus what you get as a small charge for such captive generation. And more distribution companies are now realizing the fact that the demand growth is such that their infrastructure will not be able to keep pace with. So regardless of whether we have surplus capacity in the country, the fact is very soon in these metropolitan areas and urban areas where the growth is much faster than anywhere else, it will be a challenge to keep up with the growing demand that is coming for distribution. So in a nutshell, and also let me, before I conclude, the trigeneration technology that at least that has come about here, and which was the thing that we installed in All India Institute, uses lithium bromide as a coolant, which actually is neither has CFCs or has any global warming potential. So it actually ticks all the boxes. It increases your efficiency to almost 90% as compared to any other fossil fuel or a renewable energy source. And more importantly, it does not use a coolant which either harms the ozone layer or does harm to the climate. So in a nutshell, there is a big challenge for the country as a whole to provide the kind of cooling as the demand has been projected. But equally, there's a big opportunity to leapfrog technologies to get into a very high efficient technologies, both for standalone systems and also for connected systems. And I hope forums like this would help create those kind of technological knowledge and regulatory knowledge for all of us in the country to take this forward. Once again, let me thank 10th GRIHA and this forum and all of you for listening to me. Thank you very much.
Thank you, Mr. Kumar, for such an insightful address. Mr. Kumar has to leave for a meeting, so I would request Mr. Sanjay Seth, CEO, GRIHA Council, to present a small token of appreciation to him.
Before I present this to him, I just wanted to, with the permission of the chair, of course, I just wanted to, I'm taking away your role, Markus. I just wanted to, especially our colleagues from UNSW who are here, they have, ESL, have built up very fantastic business models around which they have been able to bring down the prices. And, when he's talking about the air conditioning, while the efficiencies on one hand are going up and the prices of these appliances coming down, they are playing a very, very fantastic role in doing all of this. And no subsidies involved, nothing. It's all business models which are working very well through aggregation of demand. And the man behind this whole thing is this rock star that we have as the MD of ESL. He told me that he reminded me that I should read. The second one I bought.
May I now take the pleasure of introducing the moderator of this session, Mr. Markus Wypior. Mr. Wypior joined GIZ in 2003 as a regional manager in the Asia Pacific Department responsible for energy and environment projects. In 2005 to 2010, he was sent to India for the implementation of the National CFC Consumption Phase-Out Plan and National CTC Phase-Out Plan under the Montreal Protocol on substances that deplete the ozone layer. It's a pleasure to have you here, sir. Let me now take the opportunity to introduce our speakers for the session. Dr. Anir Upadhyay, Research Fellow, Faculty of the Built Environment, University of New South Wales. Dr. Upadhyay's research mainly interrogates real-world problems related to sustainability and energy efficiency in the built environment. He has developed a new approach of climate data analysis for the built environment professionals and integrated it with emerging sensor technologies to make homeowners and building designers aware of the local climate, building energy consumption, and indoor environmental conditions. We welcome you, sir. Next speaker is Mr. Sunil Kher, Managing Director, Sevcon India Private Limited. Mr. Kher brings with him the knowledge and experience of national and international market, having worked with large conglomerates prior to forming Sevcon. He is a well-known figure in the trade, specifically for his excellence and contribution towards the growth of HVAC and building service industry in India. He currently holds the position of President for the Indian chapter and National Treasurer for ASHRAE. We welcome you, sir. And the last speaker for today is Mr. Shadab Ahmed, National Manager, Defense and Government Segment, India and South Asia, Armacell. A mechanical engineer by profession with 12 years of experience in sales and marketing in the construction industry, he represented Armacell at the Thermal Insulation Committee, CHT 27 of Bureau of Indian Standards. His areas of interest include thermal insulation, flexible elastomeric foam insulation, and acoustic insulation. We welcome you, sir. I would now request Mr. Markus to take the discussion further.
Yeah, a very warm good morning from my end, and thanks, Sanjay, to Terry to invite me to be the moderator in this session. And yeah, I'm happy to have such interesting fellow panelists here. And indeed, as you have found from the introduction, they represent various aspects of the same thing. And the wonderful and brilliant introduction we had from Saurabh Kumar, who set the stage with particularly outlining how the building sector and the cooling needs will actually put a big strain on the electricity system in the near future, already today actually, but in the future even more. And while he was putting, of course, the air conditioning system itself in the center of it, which is true, because that's consuming most of the electricity, and also because of the refrigerants having a direct climate impact, as most of these refrigerants to date are still high global warming impact refrigerants. This is in the center, but on the other hand, there are many other aspects in the building which also can reduce the need for cooling or which can improve the entire situation, starting from the building envelope, having some insulation in there, having tight windows, double glazed windows, etc. These are also very important aspects which can significantly reduce the need for cooling the building or removing heat. In Germany, we are very used to it because we know when it's cold outside, then insulation of the building helps a lot, and it brings down the cost a lot in order for the heating systems. And I was really surprised when I came first to India, which is quite some time back, and I asked why people are not insulating the houses. And they said, yeah, sir, we only have winter here for 1 month, 1.5 months. It's simply not worth it. I said, come on, but 9 months of cooling, and it's the same. And it still had taken quite some time, I think, till this percolated down into the consciousness of architects, developers, etc., that this is indeed an important aspect. I think now this is coming up. The understanding is very much improving on it, but still the willingness to also pay for this still needs to be seen, because many people who build the houses actually do not take much control how that house is built. I understand the model is that you have a building which has maybe 3 floors. Now government allows you to have 4 floors. So then a developer, a builder will approach you, and for the price of one of those flats, 4 flats now, he will build the entire house, and all you actually have to do is wait and see. And
Markus is becoming Indian now.
So once that house is built, yes, the owner gets his 3 modern flats, builder's flats, so-called. They look nice, yes, indeed. I also live in one. And 1 flat is gone, sold off to someone else. But what is then the motivation actually of the owner of the house to actually see what has gone into building that house, and what is the motivation of the builder to really invest more money in order to make this an energy efficient and, let's say, more sustainable house? So these are some of the challenges we have. And yeah, in Germany, we try to overcome it with giving a passport to the building. This is also something which is coming soon. We are working with the Bureau of Energy Efficiency on that, so that residential buildings also can get a passport, and that passport will show what energy efficiency this particular house has. And this also hopefully then will give some benefits, at least for the houses to be built, that maybe the banks then can also incentivize somehow the house owners to look more into such ways to improve the efficiency of the buildings. These are, let's say, early starts, but nevertheless, I think these are the right methodologies. I would like to structure today's discussion a bit in this way. We have this India Cooling Action Plan in a draft, which has come out on 17 September this year. It is an attempt to outline for the next 20 years strategies and measures for not only the building sector, also some other sectors, but I would say mainly for the building sector, how to bring down the energy consumption in cooling, space cooling, and of course also then addressing the issue of the refrigerants as well. And as Shadab also nicely outlined, there are ways to address it simultaneously. So you can have technologies which actually do not need fluorinated, halogenated gases. Also then can, by combining the production of electricity and also then making use of the waste heat, these are technologies which significantly bring the energy efficiency level up. Just in the case of trigeneration, it is actually 40% what you can get out of the fuel if you just produce electricity with the gas genset, but with the vapor absorption machine and the boiler, the overall efficiency of that system goes up to more than 80%. So this is indeed something which makes a big difference. And yeah, if the gas price can come down, I'm surely that this can again be an option for India. So the session should be that we have these three input presentations. I think you all have a presentation, and they will cover various aspects. We will have something on thermal storage, which is also very interesting because that again can improve the efficiency of a system. And yes, we need to look into various climate scenarios in the country, and I think we will see some stunning findings and also maybe some myths and misunderstandings related to those categorization. And last but not least, yes, we have insulation of the building, but we also have insulation of the equipment itself. And even this plays an important role. So if all the even centralized cooling machines are not maintained well, and if there is no insulation, again, we have huge losses, and this also is part of it. So we have actually three additional views here to the cooling itself in the buildings and the building itself. We would collect those inputs from the three speakers and then open up the floor for a discussion where we could then discuss how this all can actually go into the policies of the Indian Cooling Action Plan, and also what would be actually the right priorities to set. The ICAP, if you have a look at it, is a wonderful, brilliant document, but it is a political document, and it also just sets the stage. So if you really want to implement it, there is a need for prioritization of measures, and then also various other aspects come into place. Cooling, I would say, is indeed a developmental need. I think there is no way one can say it becomes a human right, in particular if you live in a climate like India. There is no way how to discuss about the need or not, and it's simply, it has to be there. Only with cooling you can improve your productivity. The absence of cooling means actually deprivation of basic human rights. So this is something which has to come. But then the way how it comes, that is still something which can be influenced, and that's the way what we need to look at. So I would like to start with Dr. Anir Upadhyay and his presentation on the climatic zones, and I'm sure you will also be amazed of some of the findings he has to present.
Oh, thank you, Markus. And it's a really good opportunity to be here. Thanks, Terry, for allowing us to co-host this whole GRIHA Summit and opportunity to present. Somehow, the mouse is not going. I trained as an architect, and I moved into a slightly different area, but this is something I'm always interested. So I'm putting architecture's perspective on designing through the context-based design. So we need to understand the context. So I put the title as the pathways to high-performance architecture. And what exactly is the high-performance architecture? So I come up with this definition. It's basically, it says it needs to be integrated with and optimized on the life cycle basis. It's not like right during the construction or in the operation. It has to look all life cycle aspects of major high performance attributes. So what are those attributes? And one of them is energy conservation. And so we have to ensure the energy conservation strategies is in place and we use it. So I don't want to read all of them, but that's what I really want to focus in this presentation. So if you look at this, this is the Trias Energetica principle. What it basically says is, first, prevent the use of energy in any kind of like design or any action you do. And the second is use renewable energy sources as extensively as possible. So that is something we need to try all the time. And then only, and finally, if still needed, then we need to use fossil fuels as efficiently as possible. And then it comes like the way we were talking here earlier about high-performance cooling systems and things like that. So usually it comes all together. But as Markus already identified, okay, and he mentioned about the building has to be built in a way so that you don't need to use excessive energy because of the problem was not addressed in the very first place, and we'll be using that kind of energy as long as that building is there. So these are the basic principles. I just wanted to start with some kind of like common understanding. And then, so in approach to sustainable architecture, pretty much like here, what you can see, later he has put a 3-tier approach. So the first is during the building design, we need to have that 3 principles. And I think we all have done, like in architecture school, this has been taught. So heat rejection, heat retention, heat avoidance. That's the approach we take. And then we go to the second, how we incorporate the passive approach through thermal mass, orientation, windows, those sort of things, and ventilation. And then only we should be using mechanical system. But somehow, some of this approach has been like lost in between. So actually, we are thinking of air conditioning from the beginning, and which is slightly problematic, and more problematic in the context of this world, where we are struggling with the energy supplies and all these things, and even the first world, they are struggling with energy supplies. So here the problem is much deeper, and this approach is not new. If you go back and look at the vernacular architecture and all these, this approach is always there. And so it slightly elaborates what's for heating and cooling. I don't need to go in detail, but this is what we have already used to practice that. So principle, in a way, like I just want to go through quick figures. So heat protection and rejection. We used to have shading device that would really help us to protect from heat or heat rejection techniques. And then we need to use insulations to reject the heat, wall insulation, roof insulation, floor insulation, and then ventilation. to, once you insulate it, and then if you have ventilation, then you can flush the heat out. And then again, the stack effect ventilation, or those different kind of approach. So pretty much like this kind of techniques has been widely used in the past, or even we know from theory. And when it comes to the heat gain, the same thing would work for heat gain as well. Because once you have that angle right, then you can get winter sun, and it will heat up your space. And that heat, again, you can trap in with the insulation, which Markus already pointed out. So it works for both different seasons. And then you will have use that as a heat rejection technology, retention technology as well. So with these fundamentals, I want to show you a figure and a picture. It is this architecture is in particularly for a hot, dry climate, and it really demonstrates what the strategy should be: light color, small windows, and skylight over there. You want to see big windows. So actually, it is rejecting heat. And in a hot climate, that particular climate, it suits well. And in hot, humid climate, you can see the different architecture. So my main emphasis here is, because of the climatic condition, you have a very different architecture. We need to understand that. We can't have the same architecture repeated in all different places. So these are the things we need to understand. And then I'm going towards now, okay, what the Indian climatic conditions are. So this is the Indian climate zone, and this also links with that cooling strategy and also ECBC, because this has been used in ECBC as well. So I just took the major cities, and on the right, you can see what are the bases. What are the criteria has been used to delineate this climate zone. And I tried to find, I spent some time trying to understand what is the science behind it to use above 30, between 25 and 30, below 25, and that humidity criteria. I could not find any scientific literature behind it. So it has been done in 1980, but we need to kind of like question, because lots of things have been done in adaptive thermal comfort in the last 20, 30 years. So it is a time to question. And also the other thing is, this has been done in 1980. I don't know like what kind of climate data has been used. So now we have climate data, and maybe this would look very different. And 2050, it would look very different. That's my kind of like take away from while looking at all the climate data. So whatever you say, like maybe hot and dry, I don't know, like maybe super hot and dry, or cold can be a bit of mild going towards composite. So all the strategies should be very different in that way. So, and now I would like to present like how I have done it. So this is something mostly engineers, architects would use, psychrometric chart. And so this is a new delineation that I have done in the psychrometric chart, which I published paper on it. And here the cold, temperature and humidity both used together to understand. It is just a kind of environmental condition. It doesn't tell you what is the comfort, but it tells you environmental condition, whether it is hot, only hot, like without any temperature, humidity impact, or comfortable or cold, either humid side or dry side. So I don't have much time to explain this in detail, but you just remember, okay, we can divide the whole thing from the temperature and humidity perspective in 9 different zones. And then I put the hourly climate data in that one, superimposing that my different delineation. This is for Ahmedabad. And I took ISRE 2014 climate data, which is being used in India at the moment. And all of a sudden, what you can see there is it is many like dominant hours of a year is fall into humid and hot humid zone. And so that looks like the impact of humidity is really high in Ahmedabad. And this is what it is. So the different color, and you can see 40% of the time in a year is humid. And then hot humid is 16%, and hot dry 10%. So humid and hot humid is really dominating, and very less time cold is. So maybe that would be slightly in the morning or at night during December and January. So this way, it is very rational. You can just put the data, you can see it, rather than just relying on someone who did whatever done in way ahead. And that is, I think, is the way to go to look at it. And actually, the Ahmedabad is classified as hot dry. So there it comes like, why that dry? Maybe because of less rainfall. But actually, the way we feel comfort, it is not dry. When you are sweating, that's not dry. That is humid. So once we understand that, it is much easier. Then what I did, I used this method to, so you can see on the x-axis, there's the 52 data points. That represents each week. Forget about month. Just look at the weekly basis, and then you can see the changes over the time. I could have done that for a day, but that would be too much. That's 365 days. So 52 is a bit of reasonable number to work with, and then week we can really understand. And when I put that superimposed with equinox, solstice, then you can clearly see that things are changing around that time. So when you say most of the time in the way climate data presented to architects is January, February, March, April. So do you think end of December and first week of January is any different? Maybe not. But when you look at when you are doing January and February, we are not telling the truth, what's exactly going on. And that's what architects need to know and design for. So in this way, you can see the change and what's going on. And then after that, what you can do, okay, you can put other factors. For example, in warm to hot period, you can clearly see pre-monsoon, monsoon, post-monsoon. Then now we can clearly link with what's happening with the other factor, rainfall, and those aspects you can build in together. That would give you a clear idea what exactly it is. So my intention here is to present the data, whatever the data has been used for building simulation, you should be able to understand what exactly that data is. So yeah, I just wanted to use this example, Torrent Research Center in Ahmedabad, designed by Nimish Patel. So look at this building. This building doesn't have many openings. And this building has been very exemplary. I think even the Terry has used this building as an exemplary project from GRIHA rating system. And when you look at this, what he come up with, he has different strategies to deal for different season, even for cooling. So that's what we need to understand. What's going on in this particular period, how we mitigate that heat. If we go to that detail, maybe the artificial system, we don't need to use a lot. But if we don't understand and use, hot, dry, don't worry about it. So that really doesn't work, because it's not like 24/7, 365 days is hot, dry. So we need to understand the variation. And this is what we want. In Gift City, near Ahmedabad, that's what we want. So we just need to think about it, whether this is, and then you can put whatever, you can put like 4 gigawatt power plant, still we can't supply heat for power for cooling, because that's completely, we are not looking at the climate, we're just going with, we're looking at other countries and then doing it all the wrong stuff. Okay, so I'm quickly go through, because I just wanted to show you how you can see these things. So this is warm, humid Chennai, and this is what you get with my approach. Yes, you can look at the top one, humid. Yes, it is humid all the time. Yes, that could be warm, humid. That's true. But if you look at down there in terms of comfort, yeah, very low level of discomfort due to cool kind of conditions, but it's pretty much like humid all the time. And Bangalore, which is really moderate type of, even within the warm humid, this is more moderate type of climatic condition here. And Srinagar is cold, but there is a little, like a small period which you may need to cool if you haven't designed well. So, but yes, that's there. You just need to understand few weeks in a year need some kind of cooling. And this is composite Delhi. It's a very complex. Yes, you have to deal both cases. In winter, it's a bit cooler. In summer, it's extremely severely discomfort in summer. So that is the highest level you can get. And so this is from ISRE 2014. This is 2050. So should be classified as predominantly hot with a brief cool period. We need to do that because the building that we designed today is for this part of the world at least 50 years. So look at that. The extremely severe discomfort has been bunched up a lot on the top. So that's what, once you know that, it's not a big deal. We know how to deal with it. So quickly conclude, what I would like to highlight is architectural design can help moderating climate. And we can do that. And we know how to do it. But we need to understand what exactly we're dealing with. And also, our response for hot and humid conditions are different, which has been practiced since time with thousands and thousands of years. And so the current climate classification of India needs to be revisited. That's what I think. And particularly for high-performance architecture. And then once we know that, it's much easier. And then the understanding of the local climate will help to develop strategies. And I'm not prescribing here. I'm not telling you, okay, if it's humid, ventilate. I don't know like whether there's a wind or not. So I'm just telling you it's a humid, you need to do something. So that's the architect's role to how to do it. But you need to understand whether it's hot and humid, those sort of things. So, so yeah, that's all. Thank you very much. And if you have any question, you can reach to me, and I'm here until tomorrow. Happy to chat more. Thanks.
Yeah, thanks a lot, Anir. I think that was really interesting. I'm sure some of the architects in the room will have some questions to you. I propose that we first have all the three presentations, and then we start the discussion. So now, Sunil, could you please present on thermal storage?
Thank you, Dr. Anir, for a very nice presentation on what I know of 5 climatic zones. And yes, they need to be probably need to be reclassified. And also on your 3-tier approach, which I guess there is a lot of awareness. And in the architecture and other system designs, that's being applied already. But yes, it needs to be taken up to a different level. Thank you, Terry. Thank you, GRIHA. Thank you, Markus, and all the members on the dais for having invited me to give a presentation on this forum. Sustainable cooling alternatives is what is our topic of the panel discussions. And also, as Markus talked about, ICAP, the India Cooling Action Plan, development of ICAP, actually, in my opinion, is a tremendous effort. And to address the issue which is so important about sustainability, because it virtually encompasses just about everything, right from comfort, which is very necessary, to including the inclusiveness, the economic growth. So all those aspects are pretty important, and ICAP, through Ministry of Energy, Environment and Forest, and Climate Change have put up this document and does adopt a very holistic approach, by including, as Dr. Anir also talked about, the active and passive technologies and strategies to address this whole concern of sustainability. And I am here today. I bring probably a different experience on the table. Other than that, the most of the people here are either policymakers or architects, and so they bring a different view, while I come from a background with a hands-on approach of almost 30 years, having dealt with all these equipments and subjects, and having seen really, though we talk about energy efficiency, how really it gets applied in the field. And there are a lot of areas that though on paper we talk about it, that how to actually make sure that it delivers on ground. So my role here in this August panel is to address the contribution of something called not-in-kind technology to talk about, and it's thermal storage, thermal energy storage. How many of you know about thermal energy storage? Well, quite a lot of them. And how many of you know about the Tesla battery-driven car? So probably almost all of you know about Tesla. And let me just talk about it, that this thermal storage in air conditioning is, I call it as Tesla of air conditioning. Is there a slide? Yeah. Slide mode? No. Can I put it on slide mode? So that, yeah. Here, is it? No. Slide mode so that it works on its own?
Yes, sir. So
This one, no, I think.
yeah. So in just
Okay. I didn't need to click. All right.
yeah. So you can just ask them; they'll change it.
Okay. So I call it Tesla of air conditioning. In the same way as we charge using electricity the battery, and then use that battery to drive the car. In the same way, in the air conditioning, you can use the electricity to charge in the form of ice. Okay? And use that ice to provide you the cooling. So the growth in terms of related to the economic growth, the way India needs to grow in terms of its GDP, the need for energy is going to be phenomenal. So this addresses ultimately the cause of sustainability. So you can use electricity to charge the ice and then form the ice, and then ice can be used to provide cooling. And how it can be sustainable? It can be sustainable in the form that you can actually use the renewable energy. So for free, you have the solar energy available. Using that solar energy, you can drive your chillers, and using those chillers, you can store that electrical energy into thermal energy in the form of ice. So I'll give you the whole issue of, probably I'll give you a little bit more better explanation of it. So all this issue that we have been talking about sustainability, we talk about the issue of global warming, we talk about the issue of ozone depletion, we talk of the issue of pollution. Of course, in Delhi, all of us know about it, but even Calcutta or Bombay is not far away from that. We talk about, and all these, the greenhouse gas emission, all these terms, all of us have heard about. And energy security, as I talked about it, if India has to grow, At 7% GDP, we need factories, we need buildings, and for that we need electrical energy or energy. And the primary source in India, almost 60 to 70% of primary source of energy is actually coal. And of course, there is an effort to actually reduce reliance on coal and shift to other sources of energy, including the renewable resources of energy like solar or wind or hydel and other biomass and all that. But presently, it's about 60 to 65% of primary source of energy in India is coal-based. And coal-based is basically a fossil fuel. And Indian coal, we were talking to the panelists outside in the reception, the Indian coal has very less calorific value. It has a more ash content. So in other words, using coal to produce electricity, it produces all that greenhouse gas emission effect and all that we talk about, the ozone depletion or global warming or pollution, and all those issues finally are related to sustainability. So if India has to grow in a manner that there is cohesiveness, there is harmonious and inclusive growth, the issue of sustainability is at the center of the whole thing. So energy security and economic growth, they're all somewhere linked to the inclusiveness, to the happiness quotient. All these things are actually related and are different sides of the same coin. So that brings us to the issue of cooling, which is essentially energy consumption by air conditioning, HVAC, heating, ventilation, air conditioning in buildings. The electricity consumption in a building or in a built environment, it consumes about 50 to 60% of energy consumption is for the air conditioning. And therefore, it contributes quite greatly to the cause of sustainability. And it is here that ICAP actually addresses this concern and therefore is hugely relevant. And my take is that the pace at which India has to grow and the pace at which we are able to set up either the coal-based thermal power plants or renewable resources of energy-based generation capacity can't be as fast because it requires funds and so many other things. And of course, there is a minimum time required to set up such facilities. The best way to deal with that would be to have the energy efficient systems, all the strategies that Dr. Anir also talked about, retention, holding it back, and then having other passive technologies. So energy efficient technologies in active or in a passive way would actually play a very pivotal role. And therefore, one of the things that I am here to talk about is about thermal storage, which is defined in ICAP as a not-in-kind technology. But trust me, having come from the ground level, I can make a statement that if whole of Delhi or if whole of India was to be cooled by district cooling, probably we don't need any further, even if Mr. Saurabh Kumar talked about, even if we are growing, our demand is going from 6,000 megawatt to 7,500 to 9,000 megawatt in Delhi, if we were able to find a way to air condition the buildings, houses through district cooling, the existing infrastructure of power generation would probably be far adequate. But somehow there are commercial interests, there are lobbies, and we end up using air conditioners. We end up having such a big connected load that, but that's a different topic of discussions. So thermal energy storage is one technology, as I said, Tesla of air conditioning, which can address this issue of, actually it's a demand-side load management tool, which could address that question. And just to give you a brief idea, what is thermal storage and how it can actually help downsize the connected load. If you look at on the screen, this picture actually is showing kind of a load profile of any building, whether it's a office, whether it's a hospital, or whether it's a hotel, so basically what it shows is that on the x-axis you have the 24 hours time, and on the y-axis you have the connected load or the air conditioning load of the air conditioning, of fans, of lighting, and the base load, which whether computers or lighting or fans, whatever. So, and the peak load, what we see here is about 1500 TR, or converted, you can convert it into a kilowatt of a connected load of a building. So somewhere around 3 o'clock or 4 o'clock, any building normally would peak. And so what we have been from ages, what we have been doing is we've been designing the building for this peak load. That means this peak load happens for maybe 3 hours in 1 year, which is about 8,760 hours. So, and we design our building, we design the air conditioning plant, of course, after having taken into account what Dr. Anir talked about, other 3-tier approach. After taking that into account, if the peak load of a building, let's say, is about 1500 TR, the designers would actually give a chiller for 1500 TR. The designers would give a connected load to meet with that 1500 TR, let's say 1500 kilowatt. And that's actually suicidal, in my opinion. But that's happening. And I will not be able to stop that. Even though, if you see, the average load is only 800 TR. All right? So, so I'll not go into the data, but the average load is actually 800 TR, but we still end up giving a connection of a 1500 TR. We give a 1500 TR chiller. So if you divide 800 by 1500, so the plant load factor, what term most of the people would have heard applies in case of power plants. So basically the utilization factor or the efficiency. So it's, you are giving a chiller of 1500 TR or a 1500 kilowatt connected load, but actually your average load is about 800 TR or 800 kilowatt. So you are actually, your utilization capacity is only 52%, that is 800 divided by 1500. What thermal storage does, basically, it's also called the off-peak cooling system. All right? So it basically shears off the peak, and during the off-peak hours, that's mornings, late evenings, and through the night, during that period, because you have the power connection available, which you would have taken for 1500 kilowatt, or you have a, so during the off-peak hours, you can use the available infrastructure of power generation to form ice. All right, the capital cost is invested, chiller is there, connected load is there. So at that, during the off-peak hours, you can use that infrastructure to form ice. And by doing that, you have shed almost 600 kilowatt. Because, and during, so you have shed 40% of the peak load. So now peak load has come down to 900 TR instead of 1500 TR. And your plant load factor, because average load would remain 800 TR, because average load is if you distribute it over the 24 hours. So the average load still remains 800 TR, and you have now with the similar thing improved the load factor to 88% or the efficiency to 88%. So that's where, this is what thermal storage can do, that instead of taking a connected load of 1500 kilowatt, you could have managed by taking a connected load of 900 kilowatt. In other words, if you had a complex and you were to add 1 or 2 more buildings without actually taking additional connected load from the distribution companies, you could have managed that. All right, so Markus is, so I'll basically just run through some of the, just for you to get a
The
better
One
idea.
Bryant Park building in Manhattan will have another cool way of saving money. Because electricity rates fluctuate throughout the day and night, power is more expensive during peak demand, usually midday. The One Bryant Park building will maximize its electricity usage through a system called off-peak cooling.
In Manhattan, we stress out the electrical infrastructure on very hot days in the middle of summer all at the same time. And it's just incredibly inefficient. So one of the unique technologies that's happening here is called ice storage. In the middle of the night, when there's very little stress on the infrastructure, we're going to use chillers to make ice all night long, like a chipmunk storing nuts for the lean times. And then in the peak of the day, we actually have cold stored up.
Inside each large tank are dozens of spiral tubes, stacked on top of each other. The tanks are also filled with water. At night, coolant from the chillers is pumped through the tubes, freezing the water solid in the container. During the day, warm coolant is pumped back through the tubes, drawing cold from the ice and chilling the coolant. The chilled coolant then goes to air handling units to cool the air. Although off-peak cooling is already being used in many buildings throughout the world, the One Bryant Park building is several years from completion.
So basically you can downsize. This is how you can store ice in such type of tanks, as you can see on the screen, and the installation is quite easy. You could also do the thermal storage from the district cooling point of view, from a water storage and a stratified water storage technology can be used. The one more thing, I just want to run one slide.
Have you ever thrown a party? You wouldn't wait to make ice for the party till people started walking through the door, would you? Of course not. That'd be ridiculous. Want to hear something 100 times crazier? You only need about 1 pound of ice per person at a party, but to keep that same person cool in their office the following day, it takes the equivalent of 150 to 300 pounds of ice. So if it's ludicrous not to plan ahead for your party, why is it the standard practice to wait until people show up to create the cooling in buildings? Especially since the cost of electricity is 2 to 3 times more expensive during hot summer days for commercial buildings. Think of it this way: if gas was $1.29 after sunset and $3.29 the next morning, when would you fill up? So get your electricity at night with the IceBank energy storage system from CalMac. IceBank allows you to create and store your building's cooling needs by making ice at night, when electric rates are substantially lower. The next day, the ice is used to cool the building, minimizing your power usage during the electric grid's most congested and expensive hours. It's like buying your ice before the party, only 100 times smarter. Storing cooling ahead of when you need it not only reduces energy costs, but can even generate income through what's called demand response. When the grid is overtaxed during the hottest periods of the day, some grid operators will actually pay you to reduce power usage during the day. That's like the grocer paying you to take the ice before the party. You can even feel great about ice storage because at night you can store renewable wind energy from the grid. Have solar? Stored cooling from IceBank can kick in when the sun's not shining. So now you're not only rolling in the green, you're being green too. And it's not just for new buildings. IceBank works with existing buildings as well. So ask yourself, are you interested in reducing your cooling costs without affecting occupant comfort, planning a more sustainable building, and becoming a green champion? If the answer is yes, start here. This could be the best deal you make all year. IceBank Energy Storage from CalMac. Cooling for a greener, smarter future.
So I will end this slide of this presentation talking about future of thermal storage. What you see on the screen is the grid of the past, where the input or the sources of energy, essentially it has been coal, a bit of hydro and bit of nuclear, and the consumption has been predominantly residential and commercial buildings. This is the grid now, what we have, where we have added on to renewable resources of energy like solar or wind or hydro, other than the fossil fuel, coal-based and the nuclear-based. And basically, the solar can actually give back and forth to the grid depending upon what is the excess of available. This is the future grid that's going to look like, which will be truly sustainable, and you can actually store using renewable resource of energy. You can actually store it in the form of ice during the off-peak period and give it back to the grid during the time when it is necessary. So, and similarly, like what you see here, you can store it. The potential for ice storage probably is far more than what we probably know about Teslas or storing it in the battery, which can only be used for the purpose of maybe cars or laptops or maybe the lighting, while the load requirement of air conditioning is much more higher. All right, thank you very much.
Thanks a lot. This was very interesting indeed, and yes, I think that's the way forward. Then we have a last presentation from Shadab, and as earlier said, this now brings into another perspective the installation of the cooling equipment itself.
Thank you, Markus. With I coming the last, I think this stage is already set for me by my previous speakers, already identifying the need for cooling and how India is going to be a growing market for the cooling systems. So what I would be focusing in my presentation would be how to have these sustainable cooling systems become more efficient by choosing the right insulation for them. This would be the flow where we'll be talking of the role of insulation, the types of insulation, what should be the criteria when you select the insulation for your cooling systems. And there are a few other parameters which I will be focusing on when you design. What are the other things which you need to consider to make the systems more efficient? We already talked about how there is a growing market for the cooling systems worldwide. But the problem is, if you see, the 15% of the energy is consumed by the air conditioning or cooling systems which we use. And the problem is 10% of the CO2 emissions are also with the use of these cooling systems. India is very nascent as far as the cooling system requirements are concerned. So it is growing, it will keep growing, and there is all the more need to conserve energy here. When you use fossil fuels, the problem is not only that the fuels are depleting, the resources are going down, but then when you burn fuels or the fossil fuels are used, you have the problems with regards to the health also, because there are harmful gases emissions with the use of these fossil fuels. Now, coming on to insulation, it is an integral part of any cooling system. Whenever you choose any type of cooling systems, whether it is a central air conditioned plant or the appliances or the air conditioners, the home air conditioners, you have to insulate them to make them efficient, to conserve energy. And choosing the right insulation would help in conserving more energy. And it is not only the thermal conductivity values of the insulation which needs to be taken care of, because whenever we talk of insulation, we only talk of thermal conductivity values. But it is not just that. These are different type of insulations available. Some of them man-made, organic, inorganic. The most common are the polyurethane forms. Everyone would be knowing that. EPS, extruded polystyrene forms, flexible elastomeric forms are the newer versions. These are the major criteria when you have to look at when you choose the insulation for your cooling systems. The line temperature, thermal conductivity values, what is the, how do you install it, whether it is installable, whether it is easy to install or not. The fire classifications, obviously. But another important thing which is normally ignored is the water vapor barriers. If you see the National Building Code, which has been recently released, they have included the use of fiberglass, puff, EPS, and flexible elastomeric forms, which can be used as insulation for your cooling systems. We all know that the best insulator known to us is dry steady air, and the thermal conductivity of dry steady air is 0.024 watt per meter Kelvin. For flexible elastomeric forms, it is 0.035. Now, whenever we talk of thermal conductivity, if we just talk about the thermal conductivity value, which I just said, for example, 0.035, if I don't mention the mean temperature, it is a partial statement. Why? Because the thermal conductivity has a linear relationship with the mean temperatures. So if the mean temperature increases, your thermal conductivity will increase. If it decreases, it will decrease. So when you talk of thermal conductivity values, you should know at what mean temperature the thermal conductivity values are being talked about. These are the typical thermal conductivity values for different type of metals which are available for insulating. If you see, puff has the best thermal conductivity value initially, and then comes the flexible elastomeric forms, then the mineral wools, and so on. Now, what is water vapor permeability, or why water vapor diffusion resistance is important is the main thing, and this is something which is, normally not, considered when you select an insulation material. In an insulation, in an cooling system, you have an ambient temperature which is at a higher temperature. The line temperatures are at a lower temperature, because of which you have temperature differences. You have a pressure difference also, and there is always a partial pressure which is exerted on the surface of insulation. This forces the water vapors present in air to ingress into the insulation material. And the dry air which is packed into the insulation material is replaced by water. And you have to see what effect is it bringing when the water vapor ingress happens. So this is just the definition of water vapor permeability, but it is more simplified by a factor where you see the water vapor permeability of dry air divided by the material. So higher the mu value, the better water vapor diffusion properties the material will have. This is what we were talking about, that there is a partial pressure which is always exerted. Now, any insulating material in this world gives you insulating effect because of the dry air packing, because that is the best insulator. Now, any metal, whether it is flexible elastomeric forms, fiberglass, puff, or EPS, they act as a medium to pack the dry air and give you the insulating effect. Now, what happens is when this water vapor ingress happens, the conductivity values will vary. And how they vary? If water penetrates, the conductivity of water is 20 times better than the dry air, which means that your thermal conductivity values will keep on increasing by 20 times. And in extreme cold areas, if there is ice formation, then your conductivity increases by 100 times, because ice has 100 times better conductivity than the dry air. Another problem which happens because of the water vapor ingress is the under-insulation corrosion. And this under-insulation corrosion is all the more dangerous with the considerable weight gain which the insulation would have done, and there might be pipe failures also because of this corrosion. This is something which you would normally see in a site which is opened after, say, 5-7 years after insulation, which means that the water vapor ingress was happening. The conductivity of the material was not the same which you initially selected. There were energy losses which were happening, but you have come to know only when you open it. So you just don't have to see the initial thermal conductivity values. Now we need to see what is the relation of the water vapor ingress with respect to thermal conductivity values. For every 1% gain in volume of the water vapor, there is a 4 to 8% increase in thermal conductivity. There's a simple relationship there. And this is the water vapor diffusion resistance properties for various materials. Now, initially, if you see, you could see that puff had a very good thermal conductivity. But if you see the water vapor diffusion resistance properties, it is not very good. It is in the range of 34 to 100, which means that the conductivity values are not stable there, and the values will keep increasing year on year, increasing your losses. The high water vapor diffusion resistance properties of flexible elastomeric forms are because of the closed cell structure. So you need to select a closed cell structure material for your cold application. Now, if you see the National Building Code 2016, they have also identified that the insulation material, and they recommend that the insulation material which you use should be non-hygroscopic, which means they should have an inbuilt resistance to the water vapor ingress. And the NBC also talks about the properties of flexible elastomeric forms, saying that the long-term efficiency of thermal conductivity is better in flexible elastomeric forms, and this is done in chapter 11, in section 9.2.4.1.1. What ASHRAE says on mu value, it says that the life of the insulation would depend on the water vapor permeance of the system. It means that the water vapor diffusion, the higher you choose, the higher mu value you choose for the metal, the longer the life of the insulation would be. Another debate is that, okay, you choose a material which has low water vapor diffusion properties, but you give some additional water vapor barriers in the form of aluminum claddings or maybe some other aluminum foils. But what if there is a small hole in the entire cladding material? Your entire system is prone to water vapor ingress through that one single hole. So they are not sufficient. So whenever you choose the insulation material, you need to see the thermal conductivity values as well as the water vapor diffusion resistance values, because they both are related to each other. And the heat flow and the water vapor ingress, they both act simultaneously because of the temperature differences. Now, we are talking of fire performance also for the insulation material. Now, you see, you choose a very good material which is sustainable, which is highly efficient, but you cannot afford to choose a material which is not fire safe. Fire safety is much more important because all your ductings, chill water pipings, they are running all across your buildings. And you cannot afford to have a material which promotes fire. So NBC talks about the fire parameters as well. They talk of using non-combustible material, but the definition of non-combustibility as per NBC is different than what we talk in other countries. Here NBC says that the combustible material is a material which burns on its own or does not, or adds heat in case of fire, which means they are not particularly talking of the BS Part 4 test, which is for non-combustibility. They are basically talking of Part 7 test and Part 6 test, because Part 7 tests the surface spread of flames, and Part 6 tells you the amount of heat release in terms of total indexes. So you should see that either the metal complies to BS 476 Part 4, which is for non-combustibility, or the class 0 rating as per the BS standards. In addition to that, you have other standards which are UL 94. Then there is BS 6853, which tells you the smoke toxicity values in case of fire. FM approvals are there. And important thing to be noted is that in spite of all these tests, the practical behavior of the metal should be that it should not drip when it is burning. That is more important. Because if the metal drips when burning, your other metals can catch fire. On health hazards, NBC talks about using a non-hazardous material, and it should not have toxic fumes. This toxic fumes can be tested from this standard, which is BS 6853, which tells you the smoke toxicity values. If you see the health hazard conditions in the NBC, they also talk of using an antimicrobial, built-in antimicrobial, antifungal product, because there is no, so that there is no microbial growth, because of which you have health hazards. And there are standards for that, which is GIN, EN, ISO 846, method A for the fungal growth and method C for bacterial growth. Now, if you see all other generics, they do have options of antimicrobial, antifungal products, but in those cases, it is mostly a coating which is done later on. So it is not the part of DNA of the product like in flexible elastomeric forms. In flexible elastomeric forms, you can have ingredients added at the time of manufacturing so that the antimicrobial, antifungal property becomes the DNA of the product itself. It is not a coating which gets washed off. These are some examples of antimicrobial, antifungal growth on the insulation material. As far as environmental friendly insulation is concerned, you have some standards there. The RHS compliant is one of them. 0 ODP, 0 GWP. There's a standard EC 842/2006. Then there's a standard on CFC, HCFC as well, which is US EPA 5021. So you need to see that the insulation material complies to these standards. Whenever you design insulation, you need to take the worst case scenario, which is the monsoon, because it is the time when you have the highest RH. And the outer surface of the insulation material is also important, which will tell you that what should be the thickness of the insulation which you are using. You don't change any parameter and you change only the outer surface. The thickness varies because of the emissivity. And this is the standard which is used for calculating the insulation thickness. This is ISO 12241, where you have relative humidity to be input, ambient temperature, line temperature, and the external surface coefficient of heat transfer, which is dependent on the surface emissivity. These are the values of external surface coefficient of heat transfer values for a black painted surface, a gray surface, and a bright metallic surface. Which means if you have designed an insulation where you have considered the surface coefficient values as 9, and then you later on cover it with an aluminum cladding, the insulation thickness might not be sufficient because of the lower surface coefficient values. This is the impact. If you see, you don't change anything. If you have a material which has 9 surface coefficient, say the insulation thickness is S. If you reduce it to 7, the insulation thickness will be 1.5 times, which was earlier. If you have aluminum claddings or bright metallic surfaces, your insulation thickness will almost get doubled. And if you have a static area, it will be triple times. The thickness has to be used triple of what you had used earlier. By attic spaces, we mean this. Not enough spaces, the air gets stagnated, and the RH in that area keeps increasing. So these are the minimum distances recommended from wall to the equipment and equipment to equipment, which should be taken care of while designing, while using the insulation and doing the insulation in buildings. That's all from my side. Thank you.
Yeah, thanks for these great 3 input presentations and also then for the introduction by Saurabh. So to wrap it up before we start a discussion is actually that we have systems which can be way more efficient, also by combining several technologies. For example, the thermal storage with the refrigeration systems. We can improve the efficiency further by properly insulating them. And we also can actually already in the design, by looking correctly into the interpretation of all the data and choosing the right design for the right climatic zones, we can already make a difference. But the question to me is, and that's what I would like to open the floor for all of you, is how can we get these changes implemented? Obviously, it will cost also some money, and as we have seen, even if the rationale is clear, I'm sure that those coatings and those materials have a certain cost. So as I said in the beginning, we have this situation where you have a house owner who doesn't control anything how the house is built because he has a builder who is doing it for him, but whose incentive is to get it actually done at the lowest possible cost in order to increase the profits. If that is the starting point, so how we can actually get there. And finally, also, we have to consider that India still has a huge part of population which cannot afford expensive solutions. And also, I think if all this would have to be subsidized, the question also would be how to do that, from where to do that. So, yeah, the question to the room and to all of us is how do we get these certainly appropriate and absolutely necessary changes implemented, and how can we stem that as people and even then as a country? So the floor is yours. Yes, sir.
Can I ask, do we need a mic? Can I ask a different question from what you have said?
Please.
Please use the mic. So, you know, everybody has been talking about cooling, cooling, cooling. But our pollution, our problem today is pollution of the air. And indoor air quality is really a major problem in houses, offices, everywhere. And I think this should be the primary concern that we all have as far as air conditioning industry is concerned. Professor Anir Upadhyay has talked about this, you know, all the parameters, but you have not included air pollution. If you did that, you'd find a completely different graph that would emerge out of this, you know, and we would require completely different technologies. So everybody is talking about air conditioning. That doesn't help us. We need to talk about how we will treat air. So cooling is, maybe it is a requirement, yes, but air pollution, removal of air pollution is a much bigger requirement. We have had systems, but nobody seems to talk about those today.
Can I answer it, Markus? Sorry, I just... All right. Do you want to treat the cause or you want to treat the symptoms?
I think we need to treat the symptoms today, not the symptom, but the problem that this is creating.
So that you want to treat the cause?
No.
You want to treat the cause.
Is some industry somewhere which is polluting things. Cars which we are using are polluting the air.
No, so let me answer you in a very simple way.
I can't talk about that, but I'm saying that air conditioning systems...
The pollution is a function of, for which this ICAP has been actually developed. See, I'll try and put it in a simple way, that with the size of India in terms of geographical area, in terms of population, India, and from the point of view of removing the poverty, everybody has to grow in life. Everybody's standard has to go up. The poor person has to go up in life. Their children have to get educated. They have to have good hospital facilities. All I'm trying to say is that India has to grow, and there has to be an inclusive growth. For that, there is need for energy, there is need for air conditioning, and because of that, this pollution is happening. You know, I mean, this if you can't wish it away, sir. If you want to wish away the pollution, well, you cannot, unless you address the cause, and the cause is energy efficiency. So you need air conditioning, you need policy intervention as what is happening, and you need to achieve the air conditioning of this space. Instead of, let's say, using 10 tons of air conditioning, we need to manage it with 3 ton or 5 ton, as Mr. Saurabh also mentioned.
This is the problem that I have been talking about. You are only talking about how much tonnage we require. Nobody has talked about what quality of air we have after it has been treated, and we
I can add to that. Actually, of course, we can add HEPA filters to the air conditioning systems. The question is, are people first willing to pay? That's again the question of affordability. The second thing is also, of course, it needs also much more maintenance. HEPA filter needs to be changed regularly, and so this also brings in more of the servicing aspects.
No, but there must be other solutions.
But there is no, let's say, these two things don't exclude each other, and as Sunil already said, it is partially causing each other, right? We have a need, and I would really say it's a developmental need for cooling in India, because it affects everything, your productivity, your well-being, everything. This consumes more electricity. As long as that electricity is produced by thermal power plants with coal, with even has high ash content, certainly the air pollution will go up. And yeah, we have growth, industrial growth, population growth, all this. And the air pollution, what we are seeing now, are also a result of all this. So I would say the the cooling is just part of it. We have a discussion on cooling and cooling in buildings, but yes, at least partially with the cooling solutions, at least with the air conditioners or even the central cooling systems, we can bring in the filters. At least the indoor quality can certainly improve.
Well, you have already said these filters can't be used because they are too expensive, too difficult to maintain, and so on. We have had air washers. I don't know why we are not talking about those as alternatives to cooling. Air washers remove the pollution and they will give us cooling. But the only problem is we need these air washers or some systems for removal of pollution even at times when we have winter. The pollution is now and we need these systems now. All the cooling systems will not help us in this. We don't run the air conditioning system like that. Yes.
Oops. Sorry, that's kind of loud. May I?
Yeah, I just wanted to, just a moment, I just wanted to, the one that I showed you, so the pollution, do you think every part of India has got the same amount of pollution that you got in Delhi? No. Correct. That's why my approach is to present a holistic picture. Once you put that in, I'll give you a very different one for Delhi. Because once you factor in all the factors, the picture will be different.
There is a pollution map of India also.
All right, no.
Which looks different.
I just use temperature and humidity to demonstrate. That's what's been used in that kind of thing. So we can add more and make a very specific to specific area. So we can go with that.
You know, some years ago at a TED talk, a gentleman called Mittal presented a talk on plants and how they clear the air. So, yeah, Kamal Mittal, yeah. So I thought that this was kind of interesting. I've just built a new factory, and so I thought I'd do the same thing. And I have to say, it really makes a huge difference. The air quality in my factory is really quite remarkably different to the outside. You walk into my factory, it actually smells different, and you take a deep breath, and man, it makes a big difference. So I have about 125 people working there. I have over 1,000 plants inside the factory building. And I can assure you it will make a difference. So perhaps you could try it too.
I live with plants.
Well, there you go. So perhaps.
Help us here.
Why not? I mean, if everybody did this, I have it in my house at home. I have them in my bedroom. I have them, everybody in my factory has taken plants home because we've sort of...
And one of the plant is called mother-in-law's tongue.
Absolutely. That stays in the bedroom.
You keep it in your bedroom.
Now, I think we all agree that air pollution also needs to be addressed. Partially, it can be also addressed within even the cooling systems or the solutions for getting cooling. But I would say it's not either or. Both are equally important. More questions here. Oh.
Yeah, my name is Yusuf. I run a green building consulting firm in Coimbatore, Tamil Nadu. My question is to Mr. Sunil Kher. Could you throw some light on the economics behind thermal storage, especially in the Indian context, because we don't necessarily have differential pricing unlike most Western countries. So we don't have cheaper power at night. I mean, we have standard tariffs. So how does the economics work in that case?
No, I mean, economics based on first cost you're talking about, or economics based on the life cycle cost?
The first cost mainly.
So if you are concerned about first cost, it's give and take. It's almost the same depending upon the load profile. It could actually be 10% more or it could be 10% less in the overall cost. If you have a flat load profile, then probably the potential to use thermal storage is not much. But if you have a peaking kind of a load profile, which most of the buildings in India have that, then the potential for economics improves. But give and take, it's not more than plus minus 10% of the overall air conditioning cost. And if you look at the life cycle cost, then it could work out much cheaper.
Okay. And also, could you throw some light on how does thermal storage work with radiant cooling, or can it work with radiant cooling as well?
It will become a little complex. It can work, but it will become complex in terms of the equipment, and because radiant cooling is a medium temperature application, where you use about 14, 15 degrees C water supply instead of 7 degrees C. So therefore, it can be used with radiant cooling, but and radiant cooling for a Coimbatore-like environment is not very suitable because it's very humid. I don't know where will it fall in 52-week position, but it is humid. So for Coimbatore-like environment, radiant cooling is not very eminently suitable concept.
Maybe one more question related to the cost.
I have a question.
Just one question to him for the cost. Is there, apart from the initial upfront cost, also a cost in maintaining? Is there a variable cost as regards to, let's say?
The maintaining cost is much more less. In fact, the very fact that this technology is a static technology, there is no moving part like chiller has a compressor, so that's a moving part, so that breaks. But thermal storage is just ice. As they say, it just freezes and it melts, does nothing. There's no moving part and has no maintenance cost. Actually, the life of it in US, they say it outlives our age. So therefore, by the time you would have replaced chiller 3 times, this fellow would still be there. So really it saves a lot on the maintenance cost. Therefore I talked about, if you are talking of life cycle cost, then it far economical. Yeah.
Yeah, I have a question. The psychrometric chart Dr. Upadhyay had shown, it showed the various zones. Is it different from what Milne and Givoni and those people have given? And the other thing which you have shown, all the 365 days data on the psychrometric chart, is it same as what climate consultant of US university shows, or is some different parameter you have used? And you have delineated cool, warm, humid. So what was your cutoff points? Is it adaptive thermal comfort or something else? I just like to know that.
So there, the way I have done it, I've taken adaptive thermal comfort.
Is it IMAC model or is it?
It's a DDS equation, 0.71. Yeah. So and then you put like plus minus 2.5. You get your band, and then on the top I superimpose humidity comfort band. You'll get more detail in my paper because I didn't get much time to explain it.
Because it did not show in your.
Okay. Yeah. No, I can share that with you. And but what is here is, it's not Milne or Givoni, whoever you look at, even Olge, they will give you prescription as a doctor. Okay, ventilate, do this and do that, right?
Olge gave us the bioclimatic.
Exactly. Yeah. Yeah, even in that one, it gives you the what you should be doing. I'm not telling you what you should be doing. I'm just telling you it is humid, it is cold, it is hot, humid. I'm not telling you what you should be doing. That's you as an architect. You decide what's the opportunity around and explore it. And based on that, I use the comfort band, and the comfort band has been derived using humidex. So far, we're just using temperature. So humidity hasn't been discussed. Even in the new ECBC, if you go and look at their paper and search humidity, it will appear 2 times, that's it, in the whole paper. 20-page paper, 2 times humidity. So all based on temperature.
No, but those bands have been defined by actually, like 4 grams per kg.
Yeah, but we're not.
12 grams, those.
Exactly, but we're not using it. If you go and look clearly.
Zone, it has been given already.
All right, yeah, we can have discussion offline. We can talk.
One question to the organizers, how much time we have. We exceeded. We also started a bit later, to be fair. We have already a nice discussion. I have the feeling it can continue, but you have to tell us because I think there are other events also lined up, right? We need to wrap it up. One more question, one last one.
You can take it over maybe.
Okay, yeah, then thanks to my panelists and Saurabh also, who had to leave, unfortunately, thanks to the organizers. I think we really had a vivid discussion, and this really gives food for thought for everyone. I think when we leave the room or have a tea or coffee, we will be around for a couple of questions, etc. But it still will, I think, continue in our thought processes, because these are all very valid and interesting options, and it can make a difference. And yes, we should, of course, bring in the air pollution as well. It's an equally important topic, and the two are even quite interconnected. With this, thanks a lot, and I give back the floor to the organizers.
Thank you, everyone, for such an intense session that we had. And I request Mr. Wypior to kindly present a small token of appreciation to our panelists. Mr. Sunil Kher.
We have to
So, yeah, this side, sir.
It might be doing front, yeah.
So these paintings showcase Gond art, which comes with the belief that good image brings good luck. The Gonds are major tribal communities of central India. The artists have used natural colors derived from charcoal, colored soil, plant sap, leaves, and cow dung. This mystical art form is created by putting together dots and lines. Now I request Ms. Shabnam Seth. Now I request Ms. Sabnam Basi to kindly present a small token of appreciation to IST moderator. So I request everyone to please come in for a group photograph, all the speakers.